Okay, hi everyone. Thanks for virtually attending my talk. I'm Michael Dinitz from Johns Hopkins University. I'll be talking about Lasserre integrality gaps for graph spanners and related problems. This is joint work with Yasemin Nazari, who's one of my PhD students, and Zheyu Zhang, one of my former PhD students who is now at Facebook. Okay, so most of this talk is about spanners. Many of you probably know what spanners are, but for those of you who don't, spanners are just graph sparsifiers that approximately preserve distances. Right? So this formal definition is here in green. Given a graph G, a subgraph H is a T-spanner if distances in H are at most T times what they were in G. Okay, and because H is a subgraph, of course, they're at least what they were in G. So this means that distances are preserved up to a factor of G. This factor up to a factor of T. This factor T is called the stretch. In this paper, this graph that I'm going to talk about is always going to be unweighted and connected. We're going to prove lower bounds mostly, so unweighted is actually stronger in that sense than weighted. And an easy lemma to do for yourself to warm up is to see that it's sufficient for this stretch condition to hold for all edges. That's one of the nice things about multiplicative stretch, is that if you make this guarantee for all edges, then it in fact holds for all pairs. Okay, so for example, here on the left you see this kind of dense, complicated original graph G, and then on the right you see a three-spanner H. Right? So the three-spanner is significantly sparser, which intuitively makes it much simpler, and all distances are the same up to this factor of 3. Right? So they're either 1, 2, or 3 times what they were. Okay, good. So, what do we want when we do spanners? Kind of the most obvious things, we want to have small stretch and we want to have few edges. Right? So this is kind of the fundamental theorem of graph spanners. I sometimes call this Theorem 0. This is due to Althofer, Das, Dobkin, Joseph, and Soares. And it kind of tells us exactly what this trade-off is. It says that for any integer k, all graphs allow a 2k minus 1 spanner with n to the 1 plus 1 over k edges. And we can actually even find that graph efficiently using a greedy algorithm. Moreover, there are graphs where this is tight. So there are graphs where every 2k minus 1 spanner has at least n to the 1 plus 1 over k edges, assuming this thing called the Erdős-Girth conjecture that I'm not going to talk about now. Okay, good. So the trade-off between stretch and size is kind of completely understood and has been since 1993, modulo the Erdős-Girth conjecture. I'll note that you clearly can't prove a theorem like this for directed graphs. Okay, this is only about undirected graphs, because for directed graphs, I could give you k and n, so what I've drawn here is k33, which has, on the order of quadratic edges, so n squared edges. And clearly, if I remove any edge from this graph, what I'm left with is not a spanner for any finite stretch, right? Because what I'm left with, there's two nodes, so for example, this node and this node, where if I remove the edge between them, the distance goes from 1 to infinity. Right? Because in G, you can get with one hop, whereas if I remove that edge, then there's just no path. Okay, so for directed graphs, you might need quadratic edges in order to have any finite stretch, right? Unlike undirected graphs. Okay, so this is a great theorem. It's kind of the cornerstone of spanners research. But there's at least a couple obvious things you might ask, right? So what if my input graph is not a graph from the Girth conjecture, right? Like what if I give you a graph, okay, we know that there exists a spanner for n to the 1 plus 1 over k, and we know there are graphs where you need that many edges, but maybe the graph I give you isn't one of those, right? Maybe the graph I give you allows much, much sparser spanners. Can you find such spanners? What kind of graphs allow it? Lots of good open questions. Lots of good questions. Also, like the opposite direction in some sense, what if this fundamental theorem doesn't apply at all? Right? What if I'm a directed graph? I still want to say something about spanners. They're still very useful objects, but I just don't have this trade-off. So what can I say? So what we're going to do in this paper, and this is not the only thing you can do, but it's a nice thing you can do, is switch our point of view from existential bounds to optimization. Right? The fundamental theorem, these trade-off theorems, are existential. Right? It says every graph allows this, and there are graphs where you can't do better. Right? What it doesn't say is that for a particular input graph, right? That's what we get with optimization. So we can consider the optimization problem, which more or less looks like I give you G, I give you T, find me the best T-spanner of G. Or best for us is going to be fewest edges, which is not the only possible choice, but is a nice choice for best. Okay, so this switches our point of view, right? Like before, these trade-off theorems, sure, like it's nice to have algorithms that construct those spanners, it's always a plus, but fundamentally those theorems are about graph theory, right? They're saying that all graphs have this, some graphs don't allow any better. Now, if we're saying I want to find the best, the difficulty is caused by our requirement of having efficient algorithms, right? We're fighting against computational limits, not against graph theoretic limits. Because of course, if computation is free, I can find the best just by trying all possible subgraphs. Right? The fundamental issue here is that we're requiring efficient algorithms. Okay, so we're going to talk about two main variants, an undirected variant and a directed variant. And I want to go kind of very quickly through the state of the art in order to kind of place our new results in context. So basic T-spanner is the name of the problem when G is undirected. Right? So I give you an undirected G and a value T, and I say find me the sparsest possible T-spanner of G. So one immediate thing you can see is that we already have a pretty good approximation, or a decent approximation, right? Because we're assuming G is connected, so opt is at least n minus 1. When T is either 2k minus 1 or 2k, right? So take T and approximately divide by 2. The fundamental theorem tells us that we can use that greedy algorithm and get a spanner of size n to the 1 plus 1 over k. Right? So the algorithm has cost n to the 1 plus 1 over k, opt is at least n. This is an n to the 1 over k approximation. Right? And I'm going to call this generic, and we can formalize this, but I'll be a little informal what I mean by that. But I'm calling it generic because we didn't really look at the graph. Right? This statement about this approximation ratio is just, I tell you n, and I say, great, n to the 1 over k approximation. Right? I'm not doing my lower bound, my upper bound aren't really kind of using any clever things about the graph. In limited cases, we know how to do better. Right? So when t equals 3 or t equals 4, this generic approximation would give us a root n approximation, because k would be 2. So BBMRY and then myself and Zayu showed that you can beat that by giving n to the 1/3 for t equals 3 and t equals 4. And actually, I think there should be tildes over those O's, because there's some polylogs that I'm not going to care about too much. Okay, there is hardness for this. So with Guy-Kreutzart's and Raz, we kind of showed that you get basically label cover hardness with 1 over t in the exponent. So 2 to the log to the 1 minus epsilon n over t hardness of our approximation. I'm not really going to go into the hardness, it's not kind of the point, but I want to mention it because we are going to use that reduction actually inside of this paper. In directed land, things are different, right? Because there is no generic approximation, right? Because I don't have these trade-off theorems, so I can't do anything kind of generically. For t equals 3 and 4, it turns out that you can use those same algorithms. In fact, both BBMRY and my paper with Zayu are really kind of about directed spanners. And sure, they give the same thing for undirected, but they're really more about directed. If you want to allow larger values of t, the best known, due to BBMRY, that same paper, is a root n approximation. And a kind of a somewhat more classical result, due to both Kreutzart's and Elkin-Peleg, is that this is label cover hard for any t. So 2 to the log to the 1 minus epsilon n hard for any t. Modulo, standard complexity assumptions. Okay, so there's a ton of open questions here, right? There's a long line of research on optimization algorithms for spanners. I've worked on it a bunch of other people have worked on it a bunch, lots of interesting stuff to do. For example, for undirected, can you do better than generic? For t be at least 5, right? So we know for t equals 3 and t equals 4, how to get n to the 1/3 instead of root n. But above 5, we're kind of stuck with the generic approximation as being our best. And for directed, what about doing better than root n? Right? What about doing better than n to the 1/3? Like, what's the right answer? Okay, so we're not going to answer that. That's kind of definitely outside the scope of this paper, but we're going to try to show the limits of one approach. Right, so one feature of all of the non-generic approximations that I showed, so BBMRY, my paper with Zayu, some of the previous work that preceded BBMRY that I didn't really talk about, they all use the same basic LP relaxation. Right? So they solve an LP relaxation, they round, they maybe do some other stuff, but it's fundamentally about rounding that LP. And so, an obvious question is, maybe I can do better by using that same LP and coming up with a better rounding scheme. So it turns out you can't. In a paper with Roby Krathgomer in 2011, we showed that for a directed T-spanner, that basic LP has a gap of basically n to the 1/3. Right? So our state of the art is root n for general T. This gap is n to the 1/3. So there's still some room for improvement there. Right? Maybe you could use the basic LP to change that root n upper bound into an n to the 1/3, but it's a very limited room for improvement. And then following up on that in 2016, we showed that for the undirected setting, you kind of get the same thing, right? So in the undirected setting, remember, n to the 1/k is the generic approximation. The gap turns out to be something like n to the 1/k plus 4. So still like basically n to the 1/k. Okay, so similarly to the directed case, what this is kind of qualitatively saying is that yes, you can squeeze maybe a little bit more improvement out of the basic LP, but not a whole lot. Right? You're not going to be able to dramatically beat the generic approximation, maybe only by a little bit. Okay, good. So another kind of obvious thing for us to try is to say, let's since that basic LP is limited, let's try to use a better LP. Right? Let's still use LP rounding, not give up on that, but use a better LP. Okay, so what is a better LP? Well, you can try to hand design a fancier LP, or you can use these hierarchies. So these LP STP hierarchies, which probably many people here know a lot about. These are also called lift and project methods. And the basic idea is that I give you a base LP, some simple or some relatively simple LP, and I can kind of define levels, or sometimes they're called rounds, but nowadays people usually call them levels. And as you go up the levels, you strengthen the LP, right? So in fact, they have this property that level n will give back the integer program. Right? So if I go enough levels up, I actually get the integral hull. On the other hand, I can't go up that many levels because it takes time about n to the O of r to solve the level r the level r LP or STP. Right? So that means I'm kind of really concerned with constant rounds if I want polytime algorithms. But maybe I allow myself quasi-polytime and I set r to log n or something like this. Totally reasonable thing to do. Right? So these hierarchies are kind of automatic ways of strengthening LPs. So they've been studied a lot. I'm not going to cite all of the related work. They're a very kind of hot topic in approximation algorithms. In particular, these three hierarchies, so Lovász-Shriver, Shirley-Adams, and then Lasserre. So it's kind of known that Lovász-Shriver is weaker than Shirley-Adams, is weaker than Lasserre. So Lasserre is the strongest hierarchy. It's an STP hierarchy, so it turns an LP into an STP. It has a nice dual interpretation as the sum of squares proof systems that I'm not going to talk about. So a cool thing. A lot of you here probably know it. If not, a cool thing to go read about. Okay, so what we do in this paper is we prove strong integrality gaps against the Lasserre hierarchy. And since Lasserre is the strongest hierarchy, also against the weaker hierarchies, against Shirley-Adams and Lovász-Shriver. Okay, so what do I mean by strong integrality gaps? Here's the formal theorem statements. Let's not worry too much about exactly decoding them. Right? The things to note are that we go up a lot of levels. Right? Like I said, for efficient algorithms, we want n or maybe log n levels. We're going up polynomial levels. And even at polynomial levels, we show for directed spanners basically an n to the 1/18. Right? So a polynomial hardness. Okay, so even for polynomial levels of the hierarchy, which you clearly cannot solve in polytime, but even if you could, you still wouldn't be able to use that to get an approximation better than about n to the 1/18, which sure, is certainly better than root n, but is not dramatically better. You know, it's not n to the 1 over 1,000 or something like this. Okay, for our undirected, we show a similar thing. So again, the exact parameters are kind of given here. But, you know, again, we go up a polynomial levels of the hierarchy, and we get something that is not too much better than the generic approximation. Okay, so this is bad news, right? This paper is all bad news. It's saying that even these super strong hierarchies, polynomial levels of an SDP hierarchy, don't let you kind of improve much over the state of the art. And I'll mention that you know, we showed you can extend these to directed Steiner network, shallow light Steiner network. This isn't just about spanners, but somehow spanners are the more interesting problem here, I think. Okay, so I'm going to kind of very quickly go through our techniques and how we prove this gap. And this is a super technical thing, so I'm really going to only give this super duper high level. I'd encourage you to read the paper or email me if you're interested. So we need a base LP to start with. We're really going to use this length-bounded flow LP that I introduced with Roby Kraftkammer back in 2011, which is really kind of a standard network design LP applied to spanners. Unfortunately, the usual way of writing this LP has an exponential number of variables that then you have to play some tricks with to solve efficiently. So we're not going to do this. We're going to instead have an equivalent LP that only has a polynomial number of variables. And it's totally equivalent to this length-bounded flow LP. You can show if and only as for each direction. So, okay, in order to define this LP, I need to define these two things. So PUV is the set of all stretch T paths from U to V. And ZUV, and I'm going super quick, so I'm running out of time, is the kind of set of fractional cuts against stretch T paths, right? So ZUV, I put some number ZE on every edge, so that for every short path, for every stretch T path, the sum of those edge lengths is at least 1. Right? So it's a fractional cut against stretch T paths. There's an exponential number of these, but you can kind of see it's a polytope, so there's only a finite number of kind of extreme points of this thing. And now I can define an LP in terms of that, right? So my LP says XCs are, you know, 0 if I don't buy the edge intuitively and 1 if I do buy the edge intuitively, but of course we're going to be fractional. So it says minimize the number of edges you need to buy, subject to I cover every fractional stretch T cut, right? Which, you know, if you think about it for a minute, you'll see means that I've bought a stretch T path in the integral case. Okay, so good, that's the LP. There's an infinite number of constraints, right? Because I have a constraint for everything, every Z and ZUV. But you can kind of convince yourself only finite of them matter, so let's not worry about it too much. Okay, so the Lasserre SDP is complicated, so I'm only going to kind of flash it up at you. But what you're doing intuitively is you're adding constraints. Right, so I have a variable for sets now, not just for a single edge, but for sets of edges. And I want the variable for these sets to kind of act like the product of the individuals. And another way to think about this is that I'm kind of inducing consistent local distributions, which is kind of a nice way of thinking about it, but I don't have time to really go into it. Okay, so it turns out this is what you get when you use the standard Lasserre thing. I'm not going to go into it. The only point to note is that I have these variables y, right? Y are my variables. And this says that when I put them all in a matrix, that matrix has to be PSD. And for every one of my original constraints, I get a new constraint, which says that some other matrix has to be PSD. You can see this matrix kind of looks like my original constraint, right? Sum over E and E of ZE. That's kind of like XE, except it's got this I union J. And this is saying that it's at least 1, is saying that when I subtract that I union J, it's at least 0. Okay, so that's what's going on. Okay, so in the past, the previous hardness results have done these reductions from label cover. Okay, why am I talking about hardness? Because the integrality gaps that we've managed to build in the past, we're using that hardness reduction, but not on hard instances. We'd use that hardness reduction on instances of unique games that have large opt, because it was then easy to argue that unique games had good fractional solutions that immediately gave us the gap that we wanted. Unfortunately, we can't do that against the Lasserre SDP because Lasserre works quite well for unique games. Of course, not enough to disprove the unique games conjecture, but like much better than we need, or much better than we want. Okay, so what are we going to do? So we're not going to use unique games, but we're still going to use this idea of plugging in a special set of label cover instances into our hardness reduction. So what instances do we do? Instances of what's called projection games, which are almost full-blown label cover, but not quite. Why? Because recently, Klumtach et al. Showed that you could build good integrality gaps against Lasserre for projection games. Okay, so now it sounds like we're done, right? We can just apply the hardness reduction to spanners. Instead of going from label cover or from unique games, we go from projection games. Unfortunately, and that is the strategy we're going to take, unfortunately, it's a pain. Right? The parameters don't work out nicely, so the reduction doesn't work together. You have to kind of redo everything and recombine things in new ways, and it becomes a pain. And that's why this paper is very long. For the no-good integral solution, that's actually the easy part. You use some extra property of this instance of CMMV, which isn't explicitly written down in their paper, but it's easy to see. For the cheap fractional solution, you have to do a whole bunch of kind of linear algebra and come up with these ad hoc arguments on why these matrices are PSD. You can do it, but that's the key technical thing. You have to decompose these things very carefully. Okay, so that's all I'm going to say. Right? There's an enormous number of details I'm skipping. This was a huge amount of work to figure out how to actually prove that those matrices are all PSD. It's a lot of work. The message, though, at the end of the day, is that you can't use these standard hierarchies to get significantly better approximations for these kinds of problems, for spanners, for a Steiner network, shallow light Steiner network, and similar things. There's obvious open questions, right? Still, I'd like to get better approximations. Maybe I just need some new technique. Maybe I can still use the hierarchies. I just need a better base LP. Totally plausible. I don't know how to do that, but that'd be very interesting. So still lots of interesting things to work on. Okay, thanks.